organizing committee. I would like to thank you very much for agreeing to give a presentation at the Theory of Particle Physics Summer School in Turkey. As you know, John Ellis is a well-known physicist. John's primary research in particle physics, they understand that from that, but also high energy astrophysics and cosmology. Much of his research concerns supersymmetry. He is actively working on search for Fiziği particles at the TBAE and is astroparticle dark matter. John, in this hall there are approximately 55 students. They are very excited, and if you start your presentation, we will be very pleasure. Thank you very much.
Invitation to spend some time with you. I'm sorry that I couldn't come in person, but I'm very glad to at least be able to see you on the screen. Let me just adjust my presentation. So, how is that?
Good.
Okay. So, this morning I'm going to be talking about the Higgs boson and what may lie beyond it in particle physics. So I'll start off by talking about where we are in terms of exploring the couplings of the Higgs boson to other particles. And that will lead me on to discuss various mysteries associated with the Higgs boson, which I'll discuss in some detail. And those and other things like dark matter provide plenty of motivations for thinking there must be physics beyond the standard model waiting to be discovered. So then I will discuss some ways to look for this new physics. One technique is to use the standard model effective field theory, which I will explain. Another one is to look at specific anomalies in the present data. And so I'll spend a bit of time focusing on the anomalous magnetic moment of the muon. And then, of course, there's phenomena out there in the universe that we don't yet understand, in particular dark matter. So that's the program for the lecture. So on this slide here, I summarize the status of the standard model. So we got a bunch of fundamental matter fermions. So the gauge group is SU3 equals SU2 cross U1. And if you look at the top half of the slide, you get the impression that the quantum numbers of these particles look like kind of random numbers. Things that we would like to understand better is what explains those numbers, what explains the spectrum of particles in this standard model. So in the bottom half of the slide, I've written out the Lagrangian of the standard model in the way that you can see it on the T-shirt. So the top line describes the gauge interactions, Maxwell's equations, and so on. The second line describes how the gauge interactions work on the matter fermions. And the two bottom lines, those are the bits that involve the Higgs boson, represented here by the field of phi. So there's the Yukawa interactions between the Higgs and the fermions, and at the bottom we have the Higgs kinetic term, dv phi squared, and the Higgs potential. So the two top lines were tested with an accuracy of a mil or better before the NHC, in particular experiments at that CERN. And we're now testing the two bottom lines of the Lagrangian in experiments at the NHC. So this is a summary of where we are. So this is a compendium of measurements at the NHC, and the theory shown here in grey is compared with measurements at various different central mass energies. And along the horizontal axis, we've got production of many different types of particles, WZs, top quarks, jets, and so on and so forth. And everything seems to agree between experiment and theory. And that's in particular true for the production of the Higgs boson, which I've highlighted here in red. So what do these measurements of the Higgs boson tell us about it? So, since the Higgs boson is connected with the way that other particles get their masses, we expect that the couplings can scale with the mass. And here on this plot, there's a compendium of measurements of the couplings of the Higgs boson on the vertical axis to various different particles. The masses are given on the horizontal axis. So the standard model prediction is that the couplings should lie along this dashed line, and as you can see in the inset at the bottom, that prediction works extremely well. And when I first saw a plot of this type a few years ago, my then student and I, Teorik, and I wrote in a paper that this particle walks and quacks like a Higgs boson. And 12 years later, that's still the case. So now I wanted to introduce a couple of emerging frontiers in Higgs physics, which I think you might be interested in. So, towards the end of last year, the Atlas and CMS collaborations announced evidence for the decay mode Higgs into Z plus photon. So the evidence is not particularly strong at the moment, still it's about 3 standard deviations. And the signal is somewhat larger than the standard model value. Together with some colleagues, we evaluated the expected strength of the signal to next to leading order in QCD. We found those corrections to be pretty small. And what's the interpretation of the fact that the signal for Higgs, Higgs into Z gamma, is somewhat larger than the standard model? Well, very likely it's just statistics, but it's also possible that there may be some beyond the standard model physics hiding there, and there have been quite a number of papers, one I cited here, which explore that possibility. So this is a little bit more detail on the QCD corrections to Higgs goes to Z gamma. So here I've written out some of the next to leading order diagrams that you have to evaluate. So the next to leading order QCD increases the cross-section by a factor of 2. But it also introduces interference with QCD background. And in this plot here, I show the next to leading order effect on the cross-section, but I also show the effects on the interference. But these interference effects have been amplified by a factor of 10 so that you can see them. The overall interference effects are at a level of 3%, not sufficient to change substantially the apparent excess in Higgs to Z gamma that's been observed. So, wait and see. Another emerging frontier in Higgs physics is the search for higher order Higgs couplings. So the standard model Lagrangian includes a trilinear Higgs coupling, and it also includes a quartic coupling of 2 vector bosons to 2 Higgses. So the trilinear coupling appears in the Higgs potential, and the VVHH coupling appears in the kinetic term of the Higgs. Now in the standard model, these couplings are directly related to the mass of the Higgs and the mass of the W, in the case of the trilinear coupling, and to the VVH coupling in the case of this quartic coupling over here. So any absence or modification of these couplings would destroy the consistency, i.e. the normalizability of the standard model. On the other hand, they could be modified if there are higher order terms in the effective real theory, which I'll come back to later on. For example, an H to the 6th term would modify the trilinear coupling, and a coupling of this type would change the VVHH coupling. So experimental analyses are now emerging. They typically typically parameterize them by coupling modifiers, kappa, and measuring these modifiers and checking whether these couplings also agree with the standard model is one of the next frontiers in Higgs physics. So these are some diagrams for double Higgs production, to which both of those couplings contribute. And down below here are some diagrams that contribute to single Higgs production, modifying it through radiative corrections. So here from a while back is an Atlas search for the triple Higgs coupling. So they established a limit on double Higgs production. They also looked at possible effects of radiative corrections on single Higgs production. And they got a constraint on the trilinear Higgs coupling modifier kappa lambda, which is interesting. It's not particularly strong, but it was the first effort. The coupling was consistent with the standard model, but with a significant uncertainty. Now, something that caught my attention in the last few months has been some analyses by CMS and by Atlas, which also look at the two-vector, two-Higgs coupling. And it turns out that that's actually quite strongly constrained by the existing searches on the two-Higgs production. And in fact, both Atlas and CMS claim something like a 5 sigma exclusion of kappa 2b being 0 if the other Higgs couplings have their standard model values. So this is a plot from CMS. These are some plots from Atlas. So as I said, the possibility that this vector-vector Higgs-Higgs coupling vanishes is excluded at something like the 5 sigma level. So standard model wins again. Now all of these Higgs couplings will be measured more accurately in the future, and there will be many studies of the accuracy with which the coupling modifiers can be measured, either at the future high luminosity LHC runners or subsequent accelerators. And this is a plot taken from this report produced with the European Strategy Review a while back by my namesake Keith Ellis and collaborators. Okay, so let's step back a bit. So we found the last ingredient in the standard model, and as far as we can tell, the Higgs boson behaves as predicted in the standard model. So some people might say, okay, great. So the standard model has been completed. We know everything about the visible matter in the universe. Let's go off and do some other science. Well, I would say that establishing the validity of the standard model is just the beginning. And I use this quotation from a poem by T.S. Eliot: to make an end, i.e. find the last particle in the standard model, is to make a beginning. The end is where we start from. And now we can move on and think about what lies beyond the standard model. So for that purpose, I based myself on this old movie with James Bond, which I don't know if you've ever watched this movie, but it has a final scene actually in Istanbul. Anyway, according to the movie, the world is not enough. So I modify it a little bit. I modify the two main characters, and I give you 007 reasons for thinking that the standard model is not enough. So one issue is that when you calculate properties of the vacuum within the standard model, you find it's unstable. The standard model doesn't explain the dark matter. It doesn't explain the origin of matter. It doesn't explain the magnitudes of the different particle masses. And all these are issues which we can hope to address with the LHC. And then there are other issues culminating in making a quantum theory of gravity, which may be lying beyond the LHC. So many of these outstanding issues have to do with the Higgs. And I would like to emphasize that everything about the Higgs boson is puzzling. So here I've written out terms in the Lagrangian which involves the Higgs field. So here we have the coupling of the Higgs to fundamental fermions, the so-called Euclidean couplings. And we don't know why these couplings have the values they do, why there's such a tremendous hierarchy of fermion masses. We don't understand the origin of CP violation. So all these issues come in the category of the flavor problem. And I'm afraid I don't have anything useful to say about that in this talk. And the next term is the Higgs mass term, which is given by this parameter mu. So we really don't understand the magnitude of mu. We don't understand why mu is so much smaller than the Planck scale associated with gravity. That's the so-called hierarchy problem. And we don't understand what happens when you do calculations of quantum corrections. Because these quantum corrections seem to be massively larger than the actual value of the Higgs mass. And so that gives rise to what's often called the naturalist problem. How do we control radiative corrections? Then we have the Higgs-Porting coupling, which is essential for the stability of the electroweak vacuum. But if you extrapolate the standard model to high scales, you find that this coupling changes sign and the electroweak vacuum is no longer stable. I'll come back to that point in a moment. I've also put here a possible constant term in the standard model Lagrangian. I remind you that when the Higgs chooses its vacuum expectation value, the energy in empty space changes by many, many, many orders of magnitude more than the density of energy in empty space as measured by astrophysicists, the so-called cosmological constant of dark energy. We really don't understand why, when the Higgs vacuum changes, it finishes up with this very small value of the cosmological constant. And there might be additional terms in the Lagrangian, I'll come back to that later. So, Eric already mentioned supersymmetry, which I have to confess is my favorite scenario for what physics may lie beyond the standard model. And there's been many motivations over the years, like the naturalness of the small Higgs mass, like making grand unified theories, like string models, like dark matter, and as I'll discuss later, G minus 2 of the mirror. But I would argue that the first few years of LHC operations provided many additional motivations for supersymmetry. One is that supersymmetry naturally stabilizes the electroweak vacuum. Another is that it predicted correctly the mass of the Higgs boson, and it predicted correctly that the Higgs couplings should be similar to those in the standard model. But I personally got interested in supersymmetry over 40 years ago now, from arguments considering the naturalness of the hierarchy of mass scales, and in particular, loop corrections to the Higgs mass. So here I've written the two simplest diagrams that contribute to the quantum correction to the Higgs mass. Diagrams involving fermions, diagrams involving bosons. Now both of those sets of diagrams are quadratically divergent. And if there's no new physics until some high scale lambda, that gives you potentially an enormous potential to the mass of the Higgs. However, those quadratic divergences are cancelled if you have a specific relationship between scalar and fermion couplings, which is exactly what is predicted in supersymmetry. And in fact, we know that in supersymmetry, not only are the quadratic divergences between these diagrams cancelled, but also all modes of perturbation theory and there are many other divergences also cancelled in supersymmetry. So, look, that was 40 years ago. How about this issue of the stability of the electroweak vacuum? So this is a sort of sketch which shows you on the horizontal axis, roughly speaking, the magnitude of the Higgs field. And we know that, like everything else, the Higgs field has quantum fluctuations. And we're over here, where this red ball is located. But those quantum fluctuations could cause us to change the value of the Higgs field. And that's a concern, because in the standard model, if you do the calculations, you find that there is a lower energy state with an ultra-dense Higgs field. And if we were there, then the universe would just collapse, more or less instantaneously, in a big crunch. So how could we prevent tunneling through the barrier? Or indeed, how could we prevent the Higgs field from fluctuating over the barrier in the very early universe? So the only way is to make the barrier infinitely high, and that's exactly what happens in supersymmetry. Supersymmetry guarantees that the effective potential is positive, definitely. So this instability of empty space depends on the masses of the Higgs boson and the top quark. These are examples of diagrams that contribute to the normalization through the top quark. So, according to LHC measurements, we're not in a stable region down here. We're not actually in a highly unstable region up there. But we're in a region where the vacuum is metastable, so it has a lifetime which is longer than the age of the universe so far, just as well, because we're here. Okay? But it does look as if the universe may collapse in the future. And here's some more details of the calculations, which I've taken from papers by Butazzo et al. And Franceschini et al. I've plugged in the latest experimental values of MT, MH, and alpha S, which is also an important element. And we find that this instability will kick in somewhere around 10 to the 10, 10 to the 11, 10 to the 12 GeV. So, okay. Of course, we would like more precise LHC measurements to pin down this instability. In the meantime, we theorists should try to think of some way to stabilize the electroweak vacuum on this azimuth supersymmetry with a great way to move. Okay, but let's just sort of change our focus a little bit and ask ourselves, in general, how do we look for new physics beyond the standard model? And I'd now like to spend a bit of time talking about the standard model effective field theory. So this is a way of looking indirectly for the effects of new physics. And the appropriate quotation here comes from the Chinese strategist Sun Tzu, who wrote many years ago, "The direct method may be used, so look for new particles. But indirect methods will be needed in order to secure victory. And there might also be indirect effects due to the exchange of heavy particles that you could find. The direct and the indirect lead onto each other in terms like moving in a circle. So, he was apparently thinking about future circular colliders. Who can exhaust the possibilities of that combination?" So let me just remind you about the long and glorious history of effective field theories. So, back in the 1930s, we had an embryonic theory of TBAE. But we also had Fermi's four-fermion theory of the weak interaction. And that involved four fermions coming together at a point, which is an interaction of dimension 6, which is not normalized there. And there's a lot of argument, for maybe 20 years, about the precise form that this interaction took. Whether scalar combinations of fermions or vector or even so. But then there's a general feeling that this interaction was not fundamental, but it was an indirect indication due to exchanges of massive particles. When in the 1950s, it was established that the weak interaction had the form of current E minus A interactions. And so then people said, well, no, this interaction must be mediated by massive vector bosons. And that, of course, gave motivation for figuring out how to give masses to vector particles. So, vector field theory has also played a role in establishing QCD, grammar rectifier. So, something which many people, including myself and my collaborators, have been doing is to look at the available data from LHC and other accelerators on top physics, Higgs physics, Boson physics, electric data, and analyzing those data in a unified, global way, and looking for possible effects of high-dimensional operators. So there's a lot of high-dimensional operators. And any one of those operators may contribute to several different observables. For example, one of these would contribute to diboson production, to electric precision measurements, to top physics, to Higgs physics. And if you want to get the best possible constraints on these operators, then you have to do a global analysis, and that's what we did, including 341 different measurements. So, what we found was no significant evidence for deviations from the standard model. And if you characterize the possible couplings of those dimension 6 operators by inverse powers of some new high-scale lambda, we found that lambda was constrained typically to be bigger than 1 to 10 TeV. As you can see here, there's no significant evidence that any of these high-dimensional couplings has a non-zero value. So once you've done this, what's it useful for? Well, you can think about single-field extensions of the standard model. Just adding one additional field, which might have spin 0, it might have a vector particle, or it might be a fermion. How do these data constrain the possible masses and couplings of these additional particles? So the first comment is that, as I already said, there's no significant evidence that any of these is non-zero. But let's keep an eye on it for the future. But if you assume that the couplings are unit, then you constrain the mass of these particles typically to be bigger than 1 TeV, 2 TeV, several TeV in some cases. Alternatively, you could say, well, let's suppose that the particle has a mass of 1 TeV, then how big could the coupling be? And it's typically quite small. So, for the time being, there's no significant evidence for physics beyond the standard model, but watch the space. So here's another piece of space to look out for. So this picture here shows the magnet for the Fermilab experiment measuring the enormous magnetic moment of the mule. So the magnet is on this big truck. It's just been delivered from Brookhaven, where it was used in the previous round of experiments. And this is beautiful. I'm not sure whether this is a sunrise or a sunset. This is the dawn of new physics in the muon, or is it possibly the sunset? We'll see. So as I mentioned, there was a previous experiment done at Brookhaven, and the Fermilab experiment has now announced a series of measurements which have a smaller uncertainty, entirely consistent with the Brookhaven measurement. So here's the world average. The Fermilab result confirms the previous measurements, uncertainty reduced by a factor of 2 or so. Now, before the Fermilab result was announced, there was an initiative by many theorists to provide calculations of the anomalous magnetic moment of the muon within the standard model. So what they principally focused on was using other data to estimate what the standard model contribution should be. And this diagram down here shows the one which is the most important contributing one. So this is a diagram where the photon converts into hadrons and back again. And this is directly related to the plus and minus cross-section through a photon to hadrons. And there have been many measurements of the cross-section for this process, which you can then use as inputs into this calculation, which is -2. So here's a compilation of the data in that theory analysis. So because the muon has a mass of 100 MeV, the most important data are those below 1 GeV, which you see in this plot up here. They contribute about a half of the diagram's contribution to G-2, and they also contribute less than a half of the overall uncertainty. So these theorists gathered together all the data and they gave a prediction from the standard model for what the anomalous magnetic moment of the muon should be. And that's shown here. That's this black point there of ours here, which, as you see, disagrees quite significantly with the previous Brookhaven measurement, and also, of course, there's a new from that measurement. Now, that calculation of the hadronic contribution to G-2 was data-driven. It was using data on E plus and minus goes to hadrons. But recently, there's been a great deal of progress in doing an a priori calculation using the lattice. And initially, the uncertainties were quite large, but just recently, a collaboration called BMW has produced a more accurate result, which seems to disagree with this data-driven estimate and seems to be significantly closer to the experimental measurement. Now, that result came out a couple of years ago, and subsequently, many other lattice calculations have emerged, which seem to agree among themselves and with BMW, and to disagree with the calculation based on data. Now, towards the end of last year, another element came into the discussion. So an experiment at Novosibirsk in Russia announced new measurements of the E plus E minus goes to pi plus pi minus production. And here you see their data. And their data disagree quite significantly with at least some of the previous E plus E minus data. And that's, I think, seen most clearly here. So these green and blue points here are significantly below what the Russian experiment is now finding, and that's also true for our measurements. Okay, so it's not clear whether there is a discrepancy between the standard model calculation and the experiment. If there is, then it could be explained by supersymmetry. You would need relatively light supersymmetric particles. For example, a relatively light supersymmetric partner of the muon and a relatively light dark matter particle, chi. So the Ellis collaboration has helpfully shown what masses of supersymmetric particles could explain what value of G-2. I'll come back to that in more detail in a moment. The one point I wanted to emphasize is that the LHC searches, which are often quoted as or excluding supersymmetry up to a very large scale, leave a big loophole open for a relatively light muon and a relatively light dark matter particle. So this is from an Atlas analysis, and you can see that the muon could be as light as 100 GeV if it's sufficiently close in mass to the lightest supersymmetric particle that makes up the dark matter. So this is a plot from a paper which we're about to put on the archive, where we compile the various different estimates of the possible discrepancy between experiment and theory, standard model theory. So this is the data-driven calculation, this is the BMW calculation, this is CMP3, the Russian experiment, this is another recent analysis by W et al. And down the bottom here we have contributions that could be made by different supersymmetric models. So any of these proposed discrepancies could be explained by supersymmetry. And this illustrates what sort of supersymmetric particle masses we would need in order to explain the discrepancy. So here we have muon masses, which go down to possibly 100 GeV, as long as the mass difference from the dark matter particle is small. And these are sample benchmark points around the area which is excluded by LHC searches. And any of these would be compatible with at least one or two of the present experimental determinations of the discrepancy between experiment and standard model theory of the enormous magnetic round to the muon. And any of these models could be detected in future runs of the LHC. So I would claim that supersymmetry is not dead yet, and there are prospects for testing it in the near future. So let me just finish off by talking about dark matter. So this was proposed by Fiziği in the 1930s, based on observations of galaxies in the Okulu cluster. We found that they were going around inside this cluster too fast in the sense that the gravitational field generated by the galaxies themselves would not hold them together. So he said there must be some additional invisible matter, so-called dark matter, which generates an extra gravitational field and holds the cluster together. So I think his observations were not generally believed for maybe 40 years, until in particular Vera Rubin made observations of individual galaxies and found that the stars and other stuff in those galaxies was also orbiting too quickly. So again, we need an additional gravitational field generated by invisible matter, dark matter. And I don't have time to go into it in this talk. There's been many subsequent confirmations of the idea of dark matter. So we think the dark matter would have been copious in the early universe, and it would have annihilated into standard model particles, most of it, not all of it. Now, if you want to look for dark matter particles now, one possibility is to collide standard model particles and basically reverse this annihilation process. Another possibility is to look for scattering of dark matter particles of standard model particles in the deep underground experiment. Or you could look for some relic annihilations of dark matter particles in the cosmic maze. So the search for dark matter particles at the LHC has been a very hot topic. So you don't actually see the dark matter particles directly, you see energy missing, which was carried away by invisible particles. And this is an example from a computer simulation by CMS. On one side of the detector, you've got a lot of visible energy coming out. On the other side, nothing very much, because you can't see the dark matter particles. So there have been many searches by both Atlas and CMS, but no scientists have seen so far. no sign of other new physics either. But as I emphasized a few minutes ago, there are corners of planet space where supersymmetry could be hiding, and so it's important to keep looking for supersymmetry at LHC. In parallel, of course, people are conducting these deep underground experiments to look for dark matter scattering on nuclei, and this is a compilation of very recent experimental results. So these searches are continuing. There are plans to build much larger detectors that are much more sensitive. But in parallel, people are also thinking about other possible candidates for dark matter. And I have to confess that although I love supersymmetry, I also spend a little bit of my time thinking about other experiments to look for different types of dark matter. Anyway, that brings me to the end of my talk. So far, I understand the model is doing fine, and it has no trouble explaining the visible matter in the universe. But, as I emphasized, there's plenty of reasons to think. From Higgs physics, dark matter, maybe from beyond the magnetic moment, plenty of reasons to think that there might be more physics beyond the standard model waiting to be discovered that would finally sink the standard model. Thank you very much.
Okay, is there any question? Please.
Yeah, here you find.
As far as I'm concerned, that you have mentioned now we are looking for dark matter particles, right?
Right.
So, are there any methods currently are used for this search, or are they only on the plan?
So, the LHC experiments, Atlas and CMS, are continuing to look for production of supersymmetric particles through these classic dark matter signatures. So that's continuing. There are also other ideas to look for novel signatures. Perhaps there are long-lived particles that are produced at the LHC, which could be linked to dark matter. And this is a hot topic at the LHC at the moment. And I should say that there are plans to build a next-generation deep underground detector, which would be an order of magnitude larger than the current detectors. So all this is ongoing. But as I commented here, there are other candidates for dark matter. For example, it could be that dark matter does not consist of individual identifiable particles, but it's actually composed by coherent waves of ultralight photonic particles. And one example of this is the axion. There are other examples, and there are ideas for experiments not at the LHC, which would look for the axion and these other photonic particles.
Okay, thank you. Any questions? Please.
First of all, I would like to thank you very much for your excellent presentation. And so, how would you say our approach to supersymmetry models have conceptually changed in the last 40 years since before you first started? And what else do you personally expect for the future of this theory?
Okay, that's a very good question. So I think that maybe in the past we were focusing too much on the simplest possible supersymmetric model. And this has relatively few parameters, and it's easy to parameterize experimental searches, and so everybody focused on that. But it could be that the spectrum of supersymmetric particles is more complicated than we were originally thinking. Also, I implicitly assumed, when I was talking about supersymmetry providing dark matter, I assumed that the lighter supersymmetric particle was stable, which is not necessarily the case. So it might be unstable, and that's why there's interest in looking for long-lived particles produced at the LHC. So, as I'm trying to emphasize on this slide, we can continue doing the previous types of searches, but maybe we should think outside the previous supersymmetric box and look for unexplored regions of parameter space and look for null signatures.
Right, thank you.
You're welcome.
Last question. Is there any comment? Okay. Again, thank you very much, John. Next time, I hope we will make face-to-face for your valuable presentation. Thank you very much again.
Okay, it's my pleasure, and I really do apologize for not being able to come on this occasion, but I'm just about to go to China, and I just went to Thailand. I just couldn't squeeze a visit to Turkey into my schedule. But let's keep it as an open possibility for next time.